This is AQA A-level chemistry. We're on the year 12 alkanes topic, and this is part 1 of 6 for this particular chapter. As always, I'm going to recommend that you pause as you go, try the activities for yourself, and check your own knowledge and understanding. So in this first video, we're going to focus very much on nomenclature and isomerism as specific to alkanes. We're also going to take a look at some of the properties of alkanes and reasons for them. So to begin with, some very, very simple questions trying to draw out display formula. So try these two. The important thing is to remember that the display formula means you show every single bond. You also then need to remember my easy process best provides help, meth, eth, prop, bute, pent, hex. So methane, nice and simple, a carbon surrounded by 4 hydrogens, and propane, we've got 3 carbons and we've got 8 hydrogens around them. So let's try these two. And I'm going to use colour coding here to help to illustrate where the names have come from, because I've got propane, which is a carbon chain of 3, and I have 1 methyl group coming off it. Whereas for methyl butane, I have got 4 carbons in a row, and I've got my methyl coming off the second carbon. Arguably, you don't need the 2 on this one, because anywhere you put it, if it's not on the end of a carbon chain, extending it to pent, it has to be on the second carbon. I could just as easily put it on this one and number from right to left. 2 more examples. So let's start off with the 2,3-dimethyl hexane. Well, hex is 6 carbons in an unbroken chain. I've then got 2 methyls, so it's dimethyl, 1 on the second and 1 on the third carbon. And ethyl pentane, I start with my pentane root. I've got 5 in a row. Now an ethyl group is C2H5. The only place I can put that is on the third carbon, hence there is no number in front of it. If I moved it to here, it would actually extend the carbon chain to 6, for example. So ethyl pentane looks like this. On the next few examples, we're doing it slightly differently. You've been given an incorrect name, the sort of name somebody may put down if they still have some misconceptions. So I want you to work out what they're trying to name, draw it, and then try and come up with the correct name. So 3-methyl butane. I have got 1, 2, 3, 4 in a row. There's my bute, and I've got a methyl coming off. But I've numbered it from the wrong end because actually I want my methyl group to be in the lowest possible position. So it becomes 2-methyl butane as the correct name. For 2-methyl propane, I've got my methyl group coming off. The only place that the methyl group can come off is the second carbon, because otherwise you are extending your carbon chain to 4. So actually, I don't need the 2. The correct name is methyl propane. 2 more examples. And in this one, I've got my pentane, I've got my ethyl group coming off, the only place that can be is the third, and I've got my methyl coming off in the second carbon. So I do need the number. I don't need a number for ethyl. I've got my chain correct, so we need to try to work out where it's gone wrong. And it's actually one of those key rules that was mentioned in the last series of videos, and that is that prefixes go in alphabetical order. So it's not 2-methyl ethyl pentane, it's ethyl 2-methyl pentane. On to the next one, I've got 2,2-methyl butane. So I've got my butane, I've got my 2 methyl groups. I'm missing one small thing here. If I have 2 methyls, I must say that it is dimethyl. Okay, we're going to move on to isomerism again now. We reviewed this in Introduction to Organic. We're going to look at how it fits specifically with alkanes. So what do we mean by structural isomerism and chain isomerism? So I'm going to build these answers up in a slightly different way this time, because I want you to be able to see the similarities and the differences. In both cases, it's the same molecular formula. In both cases, something is different. Now in structural isomerism, we keep it very vague. It's a different structural formula. We know there are 3 different types of structural isomerism. Chain isomerism as one of them. What is different in the structure? It's the different arrangement of the carbon chain. We're talking about the branching. So what would the chain isomers of C4H10 look like, and have a go at naming them. Now this is a duplication of an activity that was done in the previous series of videos. C4H10, the most immediate one, is butane. I can't have any others with 4 carbons in a row, but I can go down to 3 carbons in a row with 1 CH3 coming off the middle. So I've got methyl propane, and they are my 2 isomers of C4H10. Having a go now at skeletal formulas and how we might represent them. Remember, we show CC bonds, we don't include the Cs, we don't show H's. So for an alkane, it will just be sticks. And in the first instance, we have got our pentane, 1, 2, 3, 4, 5 carbons. My methyl coming off the second carbon. My dimethyl propane, I've got to show 2 methyl groups coming off my propane chain. Going to look back now at some properties of alkanes, and let's have a think about what we mean by the term electronegative, and then see if we can explain why alkanes are nonpolar. So the electronegativity is a straightforward definition. The power of an atom to withdraw electron density towards itself is a really important start, but we're not there yet. You have to mention that it's from a covalent bond. And why are alkanes non-polar? Well, the key reason is that C and H have very similar electronegativities. What would the trend in boiling points be as you increase the chain length of a hydrocarbon? This is a GCSE question. We are going to revisit it later too. But we now need to think about specific intermolecular forces. So, as chain length increases, the boiling point increases, as discussed in fractional distillation at GCSE. Why? Because the molecules are getting larger, therefore they have stronger van der Waals forces. And if they have stronger van der Waals forces, more energy is needed to overcome them. So to finish off, alkanes are insoluble in water. Why is this the case? We think about alkanes, think about oil, petrol. If I put that in water, they are immiscible. The oil floats on top of the water. Now again, we need to go back to intermolecular forces here. Water molecules are very strongly held together by hydrogen bonds. So if you're thinking about alkanes that have only got weak van der Waals forces, the idea that they can somehow prise apart the water and slip between them doesn't make any sense. It can't happen. So we don't get the dissolving. That takes us to the end of this video. Thank you for listening. Goodbye.